Hello, everyone. Welcome back. The next talk is going to be given by Professor Eric Xing. Professor Eric Xing is the president of Mohammed bin Zayed University of Artificial Intelligence and the professor of computer science at CMU and the founder of Petom Inc. He is a recipient of the NSF Career Award, Sloan Research Fellowship, as well as several Best Paper Awards. Professor Singh is a board member of the International Machine Learning Society. He has served as the program chair in 2014 and the general chair in 2019 for ICML. He is a fellow of AAAI and a fellow of IEEE. The title of his talk is on trustworthiness of machine learning algorithms and the implications in AI-driven healthcare. Let's welcome Eric.
Okay, let me first start my screen. Are you able to see my screen?
Yes.
Great. Okay, thank you very much, Panta, for the introduction. I'm going to talk about trustworthiness of machine learning algorithms. And this is a work I did at CMU with colleagues Haohan Wang and Pantao Xie. So, all right. Well, as Panta just introduced, I recently moved to Abu Dhabi to head the new university called MBZUAI. So that's where you should find me. So this is pretty obvious when I show you this logo, but the fact is that if you want to play with a machine learning algorithm and you want to be a little bit more clever in adding a small amount of adversarial noises, it is very likely that you can trick the algorithm to believe in that I'm still at CMU. So this is actually what we're worried about when machine learning algorithms are unsafe. There are actually different kinds of adversarial examples, not just by adding a small amount of adversarial noises. You can also add many other type of adversarial interferences, such as adversarial rotations, shooting the pictures from a adversarial perspective, and so forth. So this is a very, very interesting and intriguing phenomenon that started a long line of research work recently, of adversarial robustness. Recently, our work also showed some more interesting insight into why this might have happened. For example, if you project the images into a frequency domain using Fourier transformation, and then you slightly re-engineer the data, for example, by keeping the low frequency only information and reconstruct the image, which look pretty much the same as your original image. And then also keep the high frequency information only and reconstruct to arrive at this kind of a black box look like image. And then you do your classification. You apply these images to your classifier trained on the full images. Guess what? The classifier failed to recognize correctly this low frequency image. Okay, you are equally likely to make mistakes. You're actually more likely to predict the wrong label. But if you apply the algorithm or the classifier to these high frequency only components, they actually can make you the right prediction on labels. If you want to see what is in these high frequency components, it is beyond human recognition. It is not perceived by human as something meaningful, but the algorithm believes there are something there. That's a very intriguing phenomenon, which is not unique to just a small number of images. In fact, we used our criterion to scan the CFR10 testing data set, which contain a couple of tens of thousands of images. We find several hundreds of images having this kind of intriguing phenomenon where the high frequency information could deceive a classifier trained on a full image. And there are also adversarial examples present not only in image, but also in text. For example, here I show a few examples on how to deceive a machine learning algorithm to produce the wrong prediction on sentiment by changing just a few words in an original text by replacing these words with their synonyms, or by replacing the words with something that visually looks similar. Okay, so obviously this is a very interesting kind of way to produce attack on algorithms which were thought to be robust on training data. So what's going on here? So it's very interesting to even realize that our algorithm, which show good training accuracies, and maybe even show good performance on testing performance with the natural data, could actually be fooled by adversarial examples or other type of examples. So we figure that maybe there are a couple of elements that contributes to this vulnerability of the algorithm. First of all, we believe that the model you use to train learning algorithms, say classifiers, may be by itself unsafe. Here is an example. We all know that, for example, by choosing different loss function, you could arrive at different models. You could arrive at different decision boundaries, even on the same training data set. For example, here we have a maximum margin decision boundary, but equally, you can have a cross-entropy decision boundary, which gives low margin, but still correct on training data. Imagine that you have a adversarial example, which is just slightly away from the decision boundary. You could deceive this particular algorithm, but not the other one, right? And in the nonlinear cases, such phenomenon is even more often encountered. Sometimes it is known as overfitting, but it is more related to the fact that in many cases, decision boundaries are trained to be close to training points, closer to the decision boundary. In fact, it is also easy to construct various examples to fool algorithms that are not robust. Here is a adversarial example where we construct a simple case where the prediction of the label alternates between data present in one domain versus a epsilon ball of adversarial domains. And let's construct two type of error definition. One is the natural error that you obtained from the natural loss, and the other is known as the robust error, which is the worst case error when the data is epsilon away, in the epsilon ball of away from the data. Then we can actually easily show that a base optimal classifier could attain zero error on natural error, but become completely incompetent measured by the robust error, which means that it is not a very ideal classifier. But if you use another trivial classifier, which is the all-one classifier, you just predict all the label, all the input to be one, you actually could attain a optimum 50% accuracy even for the robust error. Right? So this is basically illustrating you how important it is to choose the right model on data. The other source of unsafetyness or untrustworthiness is probably even more dangerous. It is related to the very the data itself, which we termed as unsafe data. So here is a hypothesis. For every given data point, we observe that there might be two elements inside the data. One is naturally known as the semantic signal, which carries what the human believe to be the original meaning of that. But the other component refers to what is known as the superficial label. Superficial labels are not those information perceived by human to be important in the image, but they can still be correlated with your label, as I show in the next example. When you train a machine learning algorithm, the algorithm is not human. Therefore, they may or may not only focusing on the semantic information, and they maybe pick up all the information. And when the superficial information is engineered to be deceptive, then we can trick the model. So here is an example, a very classical example where the superficial features can dominate the main message. So for human being, we probably believe that these two data set is about dog and cat. But also notice that the background of these two set of images refers to outdoor and indoor. And it is unclear how to guarantee the learning algorithm learns the dog versus a cat classifier rather than the outdoor background versus the indoor background. And that's basically telling you the superficial background really can be deceiving the training algorithm. Moreover, the trustworthiness may rely on the fact that how well you can explain your outcome or explain your model. Here I have two examples and of different ways of explaining the prediction. Right? We know that this is an apple, but here we have a tight-lipped entity which may be very, very frugal in her words. And here we have a talkative parrot which may be saying a lot. So which one do you believe? And maybe a formal way to measure, the content and the amount of information in the description could be, measured by some, information theoretic, criteria, which I'm going to show in the later. But choosing what to measure and how to measure could affect the trustworthiness of the learning algorithms. And here I actually have a longer list of explainability, which goes beyond just explaining a model or explaining an inferential outcome. They can be used to explain data. They could also be expected to explain processes, which includes software engineering quality, hardwares, and so forth, or can affect the degree of trustworthiness of a ML algorithm. So trustworthiness in ML is really a very complex issue that deserves a lot of attention. Here, I want to offer some theoretical insight, giving us maybe a hint about how to deal with the issue about trustworthiness. First of all, we argue that the training objective obviously plays a very important role. And our first result offer an upper bound of the differences between the robust error versus the natural error as a function of the smoothness of the decision boundary around data that is adversarial, right? And this is a very important bound that for the first time show people how the adversarial example can drive or can deceive any type of a decision boundary, and also shows you a way about where to reduce it. For example, according to the theorem I showed in the previous page, you could design a new surrogate loss which combines two sources of error information. The first one is to minimize the natural error, which encourage the outcome of the predictor and the label to be as close as possible. But the second term forces you to form an alignment of the prediction between the original example and the adversarial example, so that you can push the boundary of the decision model further away from those separation area between the adversarial examples and the true examples. Another insight by looking into the data more carefully, as I showed earlier, is that there may exist an information spectrum underlying all data. We have done a lot of empirical study of data sets, and it seems that the low frequency component versus the high frequency component in the data is bearing more of the model the data semantics. And also when training the model typically picks up the low frequency components first during training and then the high frequency component. This has very interesting implication because that matters how long and how hard we train a model on training data. When you train it too hard, indeed, it is going to boost your testing accuracy, but it also put you into a risk of picking up a superficial information, which makes the model unrobust. And in fact, we can even show a theoretical results, which is not yet published, that more formally characterize the contribution of the source of the contribution of the superficial information to the error bound between the robust error and the true error. In fact, you have an additive term on top of your empirical risk, which characterize the ability of picking up superficial signals, by a learning algorithm. And that's the term we also want to minimize with training any classifier or any other machine learning models. Thirdly, it can be shown that information bottleneck plays an important role in qualifying different types of explanations. In fact, you can break down the information bottleneck to be consisting of two components. One characterizes the comprehensiveness of your explanation, and the other term characterizes the briefness of the explanation you may have for the outcome. And it is useful to minimize, to optimize the contribution from both sources so that you provide not just a explanation, but a explanation that is both comprehensive and succinct, characterizing the underpinning of the outcome. So with these theoretical insights and guidelines, we can probably come up with augmentation for existing machine learning algorithms to make them more robust and more trustworthy. And here I want to show you just a quick example, a few examples. We saw this already by introducing a new surrogate loss. We're able to push the decision boundary to be more robust against adversarial examples that is closer to the decision boundary. And this amounts to a very, very simple modification of any original training algorithm just by replacing the loss function to a new loss known as the trait loss. And this is a PyTorch package we published, which allows in this plug-in augmentation. And using this technique, we were able to show good empirical performances in a number of adversarial computer vision challenges. For example, in the NeurIPS 2018 adversarial version challenges, which contains 2,000 submissions and 400 teams, our approach were able to gain us the first place in both the model attack, the model-based attack and the unrestricted attack. And in fact, we have a big margin over the second player by more than 10 points. This method also helped us to rank the top place of another Google unrestricted adversarial example competition. And you can see that among many types of adversarial attacks, we were able to dominate over other contenders. It's interesting to also study whether this new loss design, the trait design, is able to handle data resynthesized from different information frequency spectrum. And we found that the trait loss function augmented machine learning algorithms is able to be more sensitive or more attentive to low frequency information compared to a vanilla model. Okay, so you can see that when we only use the low frequency reconstructed testing data to challenge the algorithm, we get a better outcome in here and here and here compared to the original model. However, it is still not perfect. We were still able to find a substantial amount of adversarial examples consisting of only the low frequency information, to be misclassified, by even the augmented machine learning algorithm. So there are still a lot of work to be done to understand how to combat certain type of challenges and adversarial interferences. We applied this technique to a number of biomedical settings. For example, we in this classification problem of melanoma, the skin cancer, we were able to get decent performance outcome, but still we have a number of cases where we were able to still deceive the algorithm using high frequency only information. So there are still more work to do. How to basically protect our biomedical imagery data to be robust, in algorithms remains an open challenge. Maybe what we see so far suggesting that only working on augmenting the training loss is not adequate to render the model to be robust. Then the second dimension to look into is data augmentation, because we argued earlier that the data itself may be unsafe. And here is an example of an easy way of augmenting the data, which is very classical. It is meant to remove the superficial information, from the training example, so that we can turn the attention of the training model to only the semantic information. And this technique is known as it's called the worst case data augmentation, which means that we recreate a data set which is generated during the training to maximize the training loss. Okay, and this recreation is dependent on a predefined set of perturbations based on the superficial features, meaning that you actually know what feature is superficial, what feature is essential. For example, you know that the background is to be ignored and the foreground is to be focused. Then in this case, you could just combine the example in such a way that you put the cats also in outdoor and you put the dogs also indoor. Then in that case, you could artificially drive the model to be focusing on only the animal, not the background. And that's basically giving you potentially a nice outcome, which renders the model to be robust against superficial information and learning only the semantic features. However, this technique, as you can imagine, has limitations. First of all, you have to know what is superficial, what is not, right? And in the event that you don't know it, then you may, unintentionally train a model which is conditioned only on a certain type of superficial information, but become confused when you have a new background. For example, in this case, whether it is indoor or outdoor, we don't know. Then we have no way to guess whether the model is going to be robust against this example or not. So that's actually again another open problem. One way to navigate through this risk could be that we not only just look into the model itself, but look into some of the intermediate phase of the training process. For example, we may want to introduce regularizers to control, the complexity of intermediate representations of data. We all know that not modern day, machine learning, computer vision algorithms rely very heavily, on transformer models, which contains a encoder phase and a decoder phase. Then during, the intermediate phases of the post-encoder representation, you can add regularizers to reduce their complexity. And that gives you the potential to remove superficial features away from the semantic features. And this is known as the square two norm over the logit. And we tried this technique, on a number of training examples, and we found that the results seems to be very promising, and we were able to obtain state-of-the-art results against many other regularization technique over perturbed data. However, when this technique is applied to radiological images, we still find that the low frequency information, may cause the model to be performing less adequately than the full information, which means that there may be other type of signals that is not fully picked up by our model, which render it to be still unrobust. Okay, now last but not least, I mentioned that explainability over black box models is a way of enhancing trustworthiness. And here in one of our recent work, which actually is presented in this year's AAAI conference, we presented a technique that breaks down this black box system into an explainer and an approximator, which are parameterized in this way by deep network models. And then we can actually, identify an information bottleneck that can be controlled by a loss function placed on top of the information bottleneck. Okay, and in this way, our outcome is coming hands in hand with a set of underlying explanations, which is both consistent but also concise. And here are just some examples, used in sentiment analysis, digit recognitions for vision pictures, and also biological examples of sequence site prediction of biological molecular activities. And you can see that in each cases, together with a improved prediction accuracy, we also offer the underlying key elements that can help to explain the outcome, which obviously could boost trustworthiness of the prediction. This is a long topic in explainability. Here we also have another line of work that offers a personalized machine learning model approach, which means that for each of the for each of the testing example, you could imagine a separate explanation models, which is in this case, the output of a generative model that takes the input of companion data together with the training example. For example, the test example may be together a pathological image plus genomic image. Then the pathological images can be used as a input as the encoder of for the generative model of a explanatory network, and then that provides you a personalized machine learning model, give rise to the outcome prediction, which again helps to explain why a particular prediction is giving certain outcomes. Okay, with that, I want to wrap up today's presentation. First of all, I shared with you some theoretical insights about the robustness, which reveals the source of untrustworthiness coming from model risk, data risk, and the need for explainability. And I offered a few remedies according to this guideline, which amounts to designing new loss functions and providing performing data and model augmentations. And on the explainability side, there are a number of different techniques to offer explainability for inferential outcomes using information bottleneck technique or the personalized machine learning models. Although I do have some other thoughts about the adequacy and the necessity of explainability in broader machine learning operation, which I may be sharing during our panel discussions. So that ends my today's presentation. Thank you very much.
Thank you, Eric, for the great talk. Any questions from the audience?
Yeah, I have a question. Hello,
Yeah, go ahead.
can you read? Professor Eric, so I think that you mentioned in your remedies part that I think in the data augmentation, you mean that maybe we can use some GAN to generate the dogs or cat images both in indoor or outdoor. I think you in your example you mentioned this. So I have a question that how can we know that in an image which parts are superficial features and or those and other parts are relevant for our task. For example, especially in medical images cases, for example, you list the skin cancer case. So for example, in the skin cancer image, how can we know which part are like superficial features and others are not, so that we can, for example, use GAN to generate the images both that are those adversary examples and those not adversary examples, so that to do the training?
Yeah, that's a very good question. In fact, I did mention that this is a limitation that we have to deal with. I believe in the absence of explicit knowledge of what is superficial, what is semantic, one way is to resort to some kind of guided randomization. For example, in biological images, imagine a X-ray or a CT scan of human organs. The cancerous region might be occupying a smaller portion of the whole images. Then you can safely assume that the larger amount of the information in the image is background. Then by a random sampling of patches in the images and do some randomization of the background, you create a more difficult data set that is challenging the algorithm in the training phase. Remember that we call it the worst case image training data perturbation. Then you want to perturb data in such a way that you challenge your training data the hardest, render it to be of say low training accuracy. In that case, you may be actually obtaining a data a model that is more robust against potentially deceiving superficial information. But again, this is an open problem that I'm not sure whether there is a concrete knowledge yet. My second approach is to suggest that forget about only the superficial data itself, but working on the intermediate representation where you may have in the transformer, in the latent representation spectrum, certain dimensions to be carrying only the superficial information, and they can be probably removed by some regularization technique in that space.
Okay, got it. Thank you, Professor.
Thanks, Eric. Any other questions from the audience? Okay, let's thank Eric again for the great talk and very insightful discussions.
Thank you very much. I'm going to start sharing.
So for the next part, we are going to move to the panel discussion. Apologize that the schedule is running behind. So we are going to start now. We are very delighted to have Professors Joyce Hu, Hengji, Yan Liu, Regis Ragnas, and Eric Xing to join this panel discussion. So let's begin the first topic. In today's talks, we hear different opinions and thoughts regarding what is trustworthy. But overall, trustworthy is still a very general and subjective topic, and many different people have different opinions regarding what we should do to achieve trustworthiness. Could you briefly talk about one or two factors that you think are most important to trustworthiness? Let's begin with Joyce.
Sure. So I think the biggest factor for trustworthiness is working with whoever is going to be the end user to get their buy-in for whatever product you end up using. Because I think without that, most likely there will be very limited buy-in.
Thanks, Joyce. Next, Heng.
Yeah, so I just want to mention 2 points. I think number one, we should never think that our automatic methods can replace any human experts. So I would really like to advocate using our tools as assistant rather than a replacement. And the other thing is, I think it's really, really important to give them some confidence estimation, like a very reliable confidence values. And then we should do some human-computer collaboration. Maybe they can give us some candidate hypotheses and we can rank them. I think that will gain their trust better. Yeah.
Thanks, Heng, for sharing his nice thoughts. Next, Yan, could you share your opinions?
Sure. So I pretty much agree with Joyce and Heng's comments. I think one thing I would like to add in here is that for healthcare application, trustworthy actually means a lot in the sense that we're working, first of all, directly with a particular industry that is significantly pays attention to the cost of a mistake. That means that there is no way we can risk any person's life just because of a particular mistake or noise in the data. So I think from that perspective, the healthcare application demands trustworthy in the sense that interpretability, robustness, and many others that we defined in machine learning domain in a more significant way. And the second point in terms of healthcare application is that that we are also working closely with mainly that we're trying to devising a solution. A lot of our algorithms models are really nice and we can publish scientific papers, but I think very much aligned with what Joyce says, that really solving what exactly the patients and the doctors, healthcare workers, their needs and what they actually need in their daily life is really important. And that means that a lot of the trustworthy may mean that the system should not be down, right? In the sense that when you have 1,000 clicks in there, then the response rate should not be lower. I think from that sense that it's really like a whole solution, not only on the algorithm level, but literally on the system level.
Thanks, Yan, for the very insightful thoughts. Next, Regis, could you share your opinions?
Sure. Building off those previous comments, I really think that understanding limitations really matter and communicating those limitations to whoever the end user is. Kind of like, I like to think about like, imagine two ways to take like an echocardiogram. You could take like a transthoracic one or a transesophageal one. Like, how does one choose? You kind of know what the limitations are and where it could work. And that relates to the earlier questions around uncertainty, working with end users. And if we have those limitations, then like trust is more narrowly defined and where it could possibly work.
Thanks, Regis, for the nice opinions. And Eric, could you share your thoughts?
Well, I've heard already all these great opinions, so I don't feel like I have a lot to add. I think as all the previous speakers mentioned, trustworthiness is a multidimensional issue that involves model, the data, the system, and more importantly also the user and also the deliverers. So it's very important to allow Apple to be compared by Apple rather than having a unfair comparison, because I don't know whether the trustworthiness of a human can be similarly defined for an algorithm, and how to basically put a human machine into a competitive site. Heng mentioned that there may be a need to consider a better vehicle of value for human machine interaction. Therefore, we are trying to own the problem of trustworthiness together rather than putting them into a competing course. Another thing I think worth mentioning is that what is lacking most in the current AI machine learning research is the attention to standardization. People are over-reliant on benchmark and leaderboards to justify algorithm or to qualify a paper. But the repeatability and the standardization and the modularization of any solution right now is not on the top of the agenda. In fact, I saw very few papers even touching upon these points, right? So maybe defining and standardizing different elements in the formation of the solutions can be something we should look into down the road.
Thanks, Eric, for the nice opinions. So following up Eric's comments, the next question is, So right now, trustworthy is very subjective, and different people have different opinions. Given the same clinical AI solution, maybe Dr. A thinks this is trustworthy, while Dr. B does not think so. Do you think it is possible to define a standard metric to measure trustworthiness objectively and quantitatively? So this time, let's begin with Yan.
Yeah, I think that that I actually thought about this question for a long while. This question is not only limited to healthcare, but actually to many industries. I think the major challenges in defining a particular standard and in a particular protocol is also because it's really we're providing a type of services rather than, okay, I have a tool or I'm just providing this system so that people are using. So when we define services, it will be very difficult to actually quantify in terms of the practical, the metrics. For example, that when we talk with some other industries, for example, in real estate, it has been long agreed that when we hire contractors, right, to renovate our house, and it just their service level is all over the world, in the sense that when you hire a plumber, that some plumber came to say that your whole system is totally wrong and you have to reset it up, and some just say it's just a small fix and pay me $10, I'll fix it, right? So I think that this really because of the challenge we're facing in terms of the specific patient we're serving, it's so personalized, each person is so different, and at the same time the level of services that we're providing, it's just so different. Than when we combine these two factors together, the complexity just making it a lot harder to actually standardize things. But on the other side, it is also a lot of roadblock in terms of the particular industry themselves. That we may face a lot of roadblock for standardization, because really just the discrepancy in terms of the service provided, the healthcare is provided, that's how a lot of the inefficiency can arise, and so that a lot of the parties can make money, and that they're just so challenging and difficult, not only in terms of the specific technical aspect, but policy-wise and also social-wise, economic-wise. I think that also will potentially bring a lot of the roadblock in there. I'm not saying it's not going to be realized. I'm just saying that we can see where are the potential challenges. Mm-hmm.
Thanks, Yan, for the very nice thoughts. Next, Joyce, could you share your opinions?
I agree very much with what Yan said as well, because even if you ask two humans now, right, we can't assess whether or not one algorithm would be trustworthy. I think if you can't quantify it, from a human perspective, I think defining some metric will be much, much harder as well, because what I may value as something that's important may not be what somebody else has, right? I suspect what will end up happening is we'll have 3 or 4 metrics. So I like to think of it as like a skyline problem, right? So in looking at which hotel we should book for a conference, right, I might look at how far away it is, how much it costs, and what other perks it may have. I think in health, in thinking about trustworthiness, we'll just have to come up with different metrics that make sense. Like one of them might be, well, how much, data privacy can we actually achieve, as an example. Another might be, well, how many clicks does it take to use, and how useful it is. And then it just becomes a trade-off in terms of what really makes sense.
Thanks, Joyce, for sharing the nice opinions. Next, Eric, could you discuss this issue?
Yeah, I thought about this for a while, and I think one thing that is missing in many of the work and discussion is that what is the boundary between a machine or an AI algorithm versus a person, right? And whether we trace we treat a AI agent to be a semi-human or to be a tool. When you drive a car, when you take an aircraft, or when you use a microscope, what kind of a trustworthiness question you ask for those instruments? But you usually are delegating the trustworthiness to the users of a microscope, and to the drivers of a car, and to the pilots of the aircraft. And then those instruments or those vehicles, have their certain quality measures, such as deaths per number of miles, say per billion miles, and whether they review the optical features of the information and so forth. Right now, I think the trustworthiness of the AI algorithm is compounded with subjective human factors and objective tool-based factors. And that actually prevents the very definition of standardization, because a human cannot be standardized. So I would really advocate a more kind of less romantic, less emotional, and more mechanical way of treating the AI algorithm. It is just a tool. It's a tool that is not too much different, from our calculator and from say, the computer we're using. Then as long as it is delivering, what it's supposed to deliver to a kind of transmitter, say a user, a doctor, then, the responsibility of the quality or the trustworthiness, can be maybe nicely divided. So this is, of course, an open question, also touching upon like policy making and human expectation, and also competing interest. For example, is the healthcare industry, willing and ready to accept, the AI solution as a aid, as a cost reducing factor, or as another sort of type of instruments and tools. So this is unclear. At this point, I think some people are viewing the AI agent to be a competitor of the doctors to the radiologist, but some are viewing them as just another, more advanced CT scanner and X-ray machines. Depending on how we use it, and maybe a clarity on how we use it should precede the discussion about the defining standardization and the trustworthiness of those algorithms.
Thanks, Eric, for the nice insights. Next, Heng, could you share your opinions on this?
Yeah, I fully agree with everything Eric has just said. I agree that we should not get too fascinated by what AI tools can do. I would like to kind of distinguish the claims or findings from our system between obvious discovered knowledge versus some controversial or like unverified knowledge. So for the former one, like, whether wearing a mask can help prevent COVID-19, that kind of claim, if we can simply provide some, experimental results, some figures, some knowledge graphs from the clinical reports, that's pretty much enough. I mean, and then the rest of the work, whether people who are reading the report really trust it or not, that's up to them. So we simply provide as rich, reliable provenance and evidence as possible. And then for the second case, if there are really some controversial findings, then I think what the machine can do at most is to provide consistent checking. So we can do, for example, within a paper, we check the between different data modalities, between the image results and text results, and then we can check to cross-document checking, and then we can then check against background knowledge, and then we give a score. So we can tell them, what's the percentage of the triples in the knowledge graph are consistent, and why, right? We give some content. And then, users can decide whether they trust the results or not.
Thanks, Heng, for sharing the insightful.
Just to add one more thing, I don't know whether any of you is using Bing, Microsoft Bing for anything. Probably not. But Bing search actually has a really nice argumentation, like a mining summarization framework. So if you ask, if you type a question like, is coffee good for your health? You will see like 2 views, yes and no, and then they give different evidence. So I think that kind of multi-view summarization is a way to go rather than, just let the machine draw determine the conclusion. Yeah.
Yeah, thanks, Heng, for sharing the nice thoughts. And Regis, could you share your opinions?
For me, the question of trustworthiness is just hard to decouple from one of effectiveness. Like, you can imagine that you had some way you can measure the value of a particular algorithmic intervention, and then you tell me this value is positive in some hard statistic. You might say where does trustworthiness fit into that? And to me, there's an implicit assumption that's at play that if things are not trustworthy, then they won't be used, and then the effect will be small, even if the algorithm is good. And so decoupling this and understanding what are the other factors in effectiveness, trustworthiness being one of them, is just very important for me, because that's the end goal that I care about, similar to what we're talking about before. That's the end task or end user.
Thanks, Regis, for the very nice opinions. I need to go to teach a class in 3 minutes. So for the rest of the panel discussion, my colleague Xuehai He is going to be the moderator. Xuehai, I'm handing over to you.
Okay, yeah, cool. Okay, so next question is, can we better educate physicians to encourage them to trust AI solutions? So let's start with Professor Joyce. So Professor Joyce, can you share your opinions regarding this issue?
Oh, I come more from having tried to do a startup with my husband in the healthcare domain. And I think, depending on the physicians you're looking at, some are very open-minded to looking at AI, and some really view it as a threat and have no interest in, no matter how you try to educate them, right? So it's sort of a bimodal distribution. I think for the ones that are already interested and are open to it, I think education can happen, and it'll take time, obviously, but I think all the Coursera courses and all the talks that go on are a good mechanism for exposing them to it. I think for the ones that are really set against it, I suspect what'll have to happen is that they'll have to retire, and then the new batch, are more open to AI.
Thank you, Professor Joyce, for sharing these thoughtful insights. So next, Professor Heng, can you share your thoughts regarding this issue?
I'm actually curious what's the algorithm ranking us for each question, trying to figure out the algorithm you're using. So I think the way to really gain trust is to engage people. So if we can allow the users to have a say in your input and output, that probably is most effective way to gain trust. So when we were working on the drug repurposing report generation system, we asked the users to give us a candidate list of drugs and the list of chemical genes they believe are related to COVID-19. So then they feel really excited because the input to the system is from them. And then when we have the output, we also ask them to manually edit the results and then report to us how much time they spend on editing. So they will say, I just spend only half hour. That's much better than they need to spend maybe months or years to read millions of papers, right? So if they see the difference and if they kind of get engaged in some certain utility evaluations, I think we will be able to make things more exciting to them. And I think maybe we can have some, so I keep talking about human-computer collaboration. I never had any smart interface can really do that. I mean, usually what we do is we show some results and they collect results and that's it. But it would be really nice to have some feedback loop, like the machine can read their feedback and it automatically convert or translate the feedback into some additional features or additional knowledge that can be used in our algorithm. And then they can see magic, like they can see the system actually is improved, and they will feel like they are part of the developers. Yeah, so it's more like a psychological battle rather than like how to educate. I think educate, this term is too arrogant. I when I was working with the biomedical experts, I never feel like I'm in any position to educate them. Just like Eric said, we are just really developing tools to help them. I mean, they are the experts. Yeah.
Okay, thank you very much, Professor Heng. So next, Professor Yan, can you share your opinions?
Sure, yeah, I'm happy to chip in my own experience so far. I think it really depends on the type of projects or the tools that we're developing. So typically there are two types, right? One is that this is the literally the doctor or healthcare worker that they are driven. For example, I work with the doctors in ICU room where they're trying to develop an anomaly detection algorithm for the ventilators. So they're very keen on this because, you know, the alarm on the ventilators, they just have been signaled all the time, and both doctors and nurses are very much frustrated with them. So I helped them to design a very simple algorithm, and they're extremely happy. And they went ahead filing a patent. They also went ahead trying to commercialize the project, and they very much believe in it. And then we also have another doctor at USC who is actually a skin doctor that they have been handling the different type of skin burn for a very long time. And they were literally chasing us to say, can you help us develop an AI tool to actually help the patients to make the prediction, or helping us making the predictions. I think they very much are already very fascinated with the idea that this particular tool can help them, and then they are very keen on this. I think a lot of them are mostly like Heng mentioned, and also I think another panelist also mentioned about the accuracy and effectiveness, right? If the effectiveness have been demonstrated, they really are very excited and very much agreed. And I would say that they don't need to be educated, they actually are the leader for this project. But at the same time, there are also other type of projects that is more, I would say that across the different type of data sets, or trying to make some particular predictions. I think from that perspective, that a lot of doctors, first of all, they don't know how to consume this particular prediction results, or how to consume this tool, and how this can help them. From the, I think that the overpopulation wise, right, it definitely makes sense. But to individual doctor, that it sometimes could potentially be very confusing. And also it asks them to make a lot of training in order to use that tool. And they'll be wondering that why I'm doing this, right? So I think from that perspective, if this is really bottom up down, then some doctors may feeling confused and may not necessarily agree with what AI can do. And even though that sometimes that it takes time, right, to convince them, and also depends on how much they focus on the negative, the mistakes that AI model can make. This can lead to potential backlog to the advances that people have made before along that direction. And yeah, I think that there's a long way that we should go, but I think the real way is really, my feeling is that is really bottom up, like solving some particular pain points of the doctors and the clinicians, and then helping them to solve one problem at a time, potentially could help us to gain more confidence and get more educated for the whole healthcare population. And then maybe by 10 years, I don't know how long this will take, and then gradually that we can conquer, I shouldn't say conquer, but at least that we can have achieve a good balance between human computer and how we can collaborate together to achieve a good healthcare service goal at the end. Mm-hmm.
Okay, thank you very much, Professor Yan. So, Professor Rajesh, could you share your thoughts on this topic?
Sure, yeah. Sometimes I think that the need for education is not necessarily like a clinical person's fault. It's more like our fault. And because the world is changing quickly, we might have like 2 years ago, here's the algorithm. We might see like, here's a different one, like use this GRU, use a tensor factorization as we saw in Jimeng's talk. And, it's a mess. And then that mess makes it challenging to communicate like, what are the limitations? What can you actually do? And so I'd say the first bit is really the onus is on us as a community to try to like distill our understanding of how things work in as simple a way as possible. So somebody else who has not like spent years thinking about data can answer these questions a bit more quickly. And once we have that, then I think like the magic is sort of gone. And that magic being gone is kind of important because once you don't think about it as like some magical device, like AI is a magical device that can do something, then you're less likely to be like, focusing on the negative examples as just mentioned, because you're like, well, I expect it to have some because I have some like understanding of like various ways or things that might exist. And sometimes those can be like things that might exist in modeling, but they also might be things that exist in data. Like a lack of imagination is kind of part of the issue. In some sense, when you collect data, you're like, well, the part of the data that I look at is the important part. And you're like, give it to a model, what does a model know about that? It could do whatever it wants. And so like, just breaking down these like implicit assumptions that are there and translating it across to people and as simple as possible is like what we need to do. And then the education bits sort of follow as a piece after that.
Thank you, Rajesh, for your insightful discussion. So Professor Eric, can you talk about this issue?
I don't have much to add. All these opinions were great. So I recall when the first iPhone, were put on the market, it was different from every phone we saw ever, right? But people don't need to be educated to take on iPhone, and then it become popular. So I think a good solution, a good product, will be received, by the users if it is really good, and no one needs to be educated. And also the algorithms, the math, everything. There's no need to tell that because it is a part of the solution, but it is not part of the deliverable, the answer. I guess from my own personal experiences of working with healthcare providers and doctors, one of the major complaints I heard is that we're solving the wrong problem and we're not solving the problems people are looking for solutions. For example, in the radiology domain, we have algorithms and models, on the leaderboards, solving prediction, classifications and all that. But the doctors actually have no interest or very little interest in those things. They were asking questions like, can you give me useful outputs for my clinical management? For example, how I'm going to triage patients, put them into different stages, and apply treatment recommendations, and so forth. They're not looking for a label that a particular image is, cancerous or not. And they may want to even know the diameter and some of the key, physical measurements of a particular, pathological region and so forth. I feel there is a mismatch between what many computer scientists are solving versus what the doctors are actually looking for. They may be not articulating what they're looking for, but we have to investigate, the needs and the problems first before we even get started a problem. So if the goal is to publish a paper, typically, we don't look into problems. We actually are really entering already a competition, for some kind of topics that is well defined. But for the doctors to be trusting your solution, to be wanting your solution, as many of the previous speakers mentioned, They are the leaders and we are the servant. Therefore, I think be open-minded and be willing to listen and be willing to do the dirty work and solving even what appear to be a trivial, tedious problem is where the magic starts. And then once this relationship, this complementarity is established, you know, the doctors, I believe, will be more willing to be receptive of our solutions.
Okay, thanks a lot for Professor Eric's great talks. So our final questions is, what's the open problems in building trustworthy AI solutions for healthcare? So Professor Joyce, can you share your thoughts on this topic?
I think the biggest one that I feel is necessary is how do you actually incorporate the human in the loop as an unsolved topic. One of the things that I find myself guilty of, right, is working on the machine learning algorithm, but in the end, most likely for them to ingest it or a healthcare worker to ingest it, they want to be involved in the process, as Hung had mentioned, right? And so really figuring out what's the best way to for them to interact with the tool, and how can we, you know, sort of a reciprocal process of them guiding the algorithm to some extent, and then us helping them as well, is a big unsolved problem, I feel, that we haven't really looked at.
Thank you, Professor Joyce. Professor Heng, can you share your opinions?
I think now I see the pattern. Usually after Joyce, it's me. Yeah, so I mentioned a little bit about what I think is worth investing our time on in terms of research in my talk. So number one, I think we should do more multimodal integration. We should look into the information the knowledge we discover from images together with the text. So we should fuse them into a comprehensive knowledge base. And the second is, I think we should go beyond the discovery. We should probably do more prediction, hypothesis ranking, so that we can accelerate the idea generation part. And then in terms of systems and applications, I would really love to have a personalized healthcare assistant, like, you know, can integrate and use more data, more knowledge, more features. My woman doctor really showed me the predictor, the classifier they are using in almost all the hospitals for breast cancer prediction. Literally, there are only 7 features. So it's talking about your gender, of course your gender, yeah, the race, and your age range, and your family history. Like just 7 very, very coarse-grained features. And if you change the number of biopsy from 1 to 2, then the prediction probability goes from like 17% to 37%, which is crazy. They need help. And it's because if they have this better classifier, they will mistreat patients, and then they will get better data, and then the system become worse. So I think, like Eric emphasized many times, instead of, you know, get addicted to this leaderboard ranking competition, I think we should invest more time to deliver our techniques so that they can really integrate that in their online system, and then they can get more real data and just keep improving the technique. Yeah, that's all I want to say. So the research side and also system side.
Thank you very much, Professor Heng, for your interesting opinions. So now, Professor Rajesh, can you share your ideas?
Sure, yeah. In general, I think that more human AI stuff, like Joyce said, is super important, particularly like things that I find that people struggle with when we talk to them about like how to present results from a model, or like thinking about things that are like correlative and interpreting them as causal, thinking about like making an intervention based on even like a simple linear model because a feature says that that is contributing risk, are all things that like I don't actually know how to solve in terms of communication to the doctor, because the model is good in the sense that it predicts well and you can use prediction to guide what's going on. But on the other hand, if someone is going to look at that model and maybe even look at like a visualization from it and be like, I'm going to do this because this risk is high, then I'd feel like extreme concern inside of me. And it's not one that's like a statistical question. The second thing that I think just really comes to mind is that, like, moving away to solving real problems can actually be a virtuous cycle, because when we start getting involved in health systems, we can start trying to understand the biases in the data collection and start trying to influence them as well. Like things like micro-randomization is happening at certain institutions, and that can really be virtuous, because then our data becomes a little bit better. It's a little bit less biased. We can build a better model and hopefully collect data that's better and appropriate for that in the future. And if we could do these things, and not just like at the site, at like a single site scale, but it's something larger than that, because we've seen from lots of recent work that individual sites have biases associated with them, and like having a mechanism to support that. So now we're talking about something even higher level, like either funding or some other organization that can help support that. I think that would go a long way into making the progress in the community much faster.
Okay, thank you, Rajesh, for your insightful discussion. So, Professor Yan, do you have any comments on this topic?
Sure. I think that all the panelists said very good things already. But since this is the last question, I just want to be a little bit, open-minded and just talking on the higher level. There's things that are very effective, that are difficult and probably mission impossible in some countries. That is really changing the policy, right? If we have the government support and some policy changes in terms of how the healthcare records should be accessed and also who to be shared with, and then I think that a lot of really good AI renovations will be able to enable. But that this will take a long time, in particular in some countries. I think in Israel, that because they have all the digital records and a lot of the privacy constraints are less, and they were able to get a lot of things faster than many other countries. And then the second hard thing is that relatively hard and could also be effective is obviously building these tools and entrepreneurship and companies. I think that I also gave it quite a long thought about this, but I think for the healthcare, working with the doctors, we really have to have the doctors and healthcare providers as the leading in innovation in order to make changes from that perspective. But I don't think that it's not necessary to say that we can't make changes, but maybe because of all these FDA regulations and all these, policies and things like that, it's very hard for computer scientists to break into this huge I guess, castle that have been built for over hundreds of years, right? But it's not mission impossible for computer scientists to go the other way around. That is from the patient perspective, that is working with the patient, making their health management easier, making things easier. And then if we break that and then building trust from the patient level, and maybe gradually that we can even break into this very difficult castle in the longer term. But I think that then, I think from the research project perspective, that everything that we did so far in terms of focusing on some specific problems, showing that AI were able to achieve good prediction results, or were able to do some type of forecasting, for example, for COVID-19 cases, that we got a lot of really exciting stories that people shared in this particular workshop even. I think that from that perspective, there are a lot of research that we can do. But leveraging research back to making fundamental changes to healthcare industry, I think we need a lot of good observations of the whole field. During this Samsung forum happened 2 years ago, I think at that time they were asking similar questions, and I gave the answer that I think that the specific population, the elderly population, especially the whole the global population, is going to becoming elderly. That means that we're facing a lot of elder people who wants to better manage their life, better manage their health, and who actually could potentially be overlooked by many of the trendy companies. And these may be the people that potentially we can help. And this can be one of the problems. Obviously, there are many other exciting problems out there, as pointed out by the other panelists. Yeah.
Thanks a lot, Professor Yan, for sharing those inspiring thoughts. So next, Professor Eric, could you share your thoughts on this topic?
Oh gosh, and open problems. There are more open problems than solved problems, as always, right? So, in my talk, I mentioned already a couple of dimensions, like the theory behind trustworthiness, the data quality, and also the algorithm. Maybe, let me throw in some controversy here, because I feel like a workshop couldn't be more interesting if there is no controversy left. I just mentioned, and many of you guys also mentioned about listening to the doctors and let them be the driver and we be the solution provider. And in fact, I cannot agree more with that. But not on every point. There is one point I actually do want to raise a controversy. Many doctors use the reason of explainability, to turn down the algorithm. In fact, explainability right now is a question asked everywhere. It's almost like a cheap shot to shoot down most of the algorithms. Here, I want to argue the opposite. I think we shouldn't be too religious about explainability or interpretability, because at least it shouldn't be, an excuse to reject innovation. That's something that I feel very deeply about. Because at the end of the day, what we care is the solution, is whether the things work or not. The explainability is sometimes serving very often a psychological satisfaction, a intellectual satisfaction, and rarely it is serving a operational satisfaction. If something that is not operationalizable, honestly, you don't need to know that, or at least there is less value of knowing that. I gave you one example, like we're not talking about the vaccine, for COVID. If you look at the history of vaccine, the first vaccine, the second vaccine, the third one, all the way starting from Pasteur, discovering the vaccine of smallpox and anthrax and so forth, it was not explainable. It worked. Okay, it saves millions of people, and then people use it. I believe the origin of the vaccine came from either the Arabic world or in China, even hundreds of years before Pasteur, and it also worked. And then people adopted it. So I would say functionality and the solution precedes the explainability. And also these days, when a doctor gives you a piece of aspirin and say it is good for your headache or it is good for your heart attack, I don't think there is explainability behind it, at least biologically or biochemically, because I was trained as a molecular biologist. I know that there are way more unknown in the biological system than that is known. So many of the existing modern day treatment in medicine does not have a physically sound explainability, at the biochemical, at the regulatory network level, but we have no problem using that. Right? So this is kind of my stone into the pond to stir some controversy that we machine learning people, we computer scientists should not be distracted by a too aggressive pressing for explainability, over the utility of our solutions.
Thank you very much. Thank you very much, Professor Eric. Thank you, everyone. So I think that's for this panel discussion. So I think Professor Eric will also make some closing remarks of this workshop. So Eric, can you make some remarks?
I don't know why I was asked that, but Peng Tao obviously are too busy with his teaching engagement, so he asked me to do the closing. I think I want to, on behalf of Pengtao, to thank, all the speakers and also the audience, and to attend this very exciting, very interesting workshop. I personally learned a lot from all the talks. I regret I couldn't speak the whole day for the talk, but I really learned from what I've heard already for the afternoon session. I also want to thank, on behalf of the speakers and attendees, to organizer Pengtao. I know there are more names on the organizer list, but I know that in fact he is the guy who did most, if not all, the work. I really think he deserves a applause from all of us for his contribution to the community. So with that, I hope everybody enjoy the rest of the day and enjoy the rest of the conference. Thank you very much.
Thank you. Also, thanks to Shihan. You did a wonderful job continuing organizing.
Yeah, I forgot to include Shihan. You did a great job, in moderating the rest of the panel.
Yeah.
Thank you, Professor.
Thank you. Bye.
Thank you very much.
Thanks all.
Great workshop.
Thanks.
Thanks everybody.
Bye.